Mike,
Excellent. I believe we are now live. Welcome, everybody. Thank you. Thanks for joining us. Happy to have you here. Mike, are these guys seeing me on a split screen and our slides up, or what does that view look like since we're doing live television?
Right now, it's just the slides coming for you.
Just slides? Okay. Probably my better side. I just want to know how animated I'm able to get during today's presentation. So while we're giving everybody the opportunity to register on, okay, I could take a look at us now. Perfect. Excellent. Thank you. I appreciate that. Welcome, everybody. While folks are getting in line and in the queue, my name is Mitchell Brourman. Let me be the first to welcome you to our live broadcast here from Pittsburgh, Pennsylvania at the headquarters of Field Environmental Instruments. It's a pleasure to be with you. As I mentioned, this is a live broadcast. We have folks who are here in our studio audience, as well as a lot of folks who are out in the virtual world. So thank you all for joining us. Much appreciated. The folks who didn't and weren't able to attend, you missed lunch earlier today, but those folks who came, we actually fed, and so thanks very much. This is a live broadcast, and it is also unrehearsed. So what you're getting is the prime run, exactly, and you're getting our best. So please indulge us as we work our way through that. I want to say thank you to the folks from Focused Remediation Seminars. I've actually coined this as a special event. For those of you who are used to joining the Focused Remediation Seminars series, this is what we've coined as a special event. And it really is sponsored by both the folks at Provectus, Field Data Solutions, and Field Environmental Instruments, which I am a part of. So, and that'll have a little bit more relevance in just a minute as we move on to the slides. Let's see, there we go. Oh, is this on? It's down. Okay, there you go. So the title for today's talk, the latest innovation in ISCO remediation technology, the creation and monitoring of sustainable and affordable continuous ISCO reactive zones. And there you have our slate of speakers. We're going to kick off with Troy Leiser from Provectus, then John Wright from Field Data Solutions is going to join us. Then Doug Gray is also going to be one of our speakers. And in between John and Doug, we're going to actually do a live demo and walkthrough of the actual trailer and the equipment that we're talking about in itself. And so we have the opportunity. The folks from Provectus were kind enough to bring their trailer here so we could do that. In addition, we hooked it up to live power, so we got a small demo running out there. We're actually going to demonstrate some of the monitoring that went along with this project. The sort of genesis of this whole idea was at Battelle recently, back in June, at 3 different places, we were talking about this very thing, and it was Jim Mueller's idea. So if this goes completely bad, we know who to blame. And a shout out to Jim, who wasn't able to come today. He's sitting with Chris Mullen back in Illinois. Shout out to Jim. It's your fault if this goes bad, and you get all the credit if this goes good, Jim. So thank you. But it was Jim's idea to take. We had just sat through Doug's presentation, and we were like, wow. He's got so much information that he could have presented, but because of the time constraints of Battelle's format, he was shrunk down. John Wright and I did an actual learning lab demonstration on the exhibit floor at Battelle, where we featured the monitoring equipment that we had out at the pilot test that you're going to hear about. And Troy was there as well. And Troy, I don't know if you presented at this specific Battelle or if it was the one before demonstrating the technology, but we thought, hey, this would be a great idea to put all this stuff together in a condensed format and put it out there for you guys to hear. And so that is the genesis of how we got to where we are today. In addition, for all you folks who stick with us, I want to let you know we were actually able to secure CEUs and PDHs for today's event, 2.5 professional development hours or 0.25 continuing education units from the American Institute of Professional Geologists, AIPG, an organization that has helped us do independent accreditation for the focused remediation seminars prior to this, and has become an ally in helping us do that. We feel an obligation to make sure that what we are doing is good content and good transfer. Obviously, we all work for companies, and we're hoping that you'll think about us when the time is right. But at the end of the day, this is about tech transfer and not just the routine sales pitch. So at the end of the day, we think that independent accreditation helps solidify that. In order to obtain those credits, and you should get a certificate from us if you stick around. You have to stick around for the whole day. Microsoft Teams production model that we're using allows us to monitor that, so you don't have to send us anything. You don't have to worry about checking in. We know all about that from your registration. But if you stick around with us for the full 2.5 hours and up into the Q&A, then you would be eligible for those credits. And we will make sure that those certificates get sent out to you accordingly. As I mentioned earlier, we are working in the sort of Teams environment. This is not the same control panel for you, those of you who are joining us virtually, that you'll see, but it is essentially the Teams format. So we have taken the liberty of excluding your microphone and excluding your camera, so don't have to worry about that. You should be able to hear us no problem. And to communicate with us, we ask that you use the chat function. And in those chat functions, you can post in there your questions on anything that comes up. We'll be monitoring that channel during the day. And if you have specific questions about an individual presentation, send those in there. We'll try to get to them during the presentation, see how the time unfolds. And then if not, we have a Q&A block at the end, and we'll sort of do a recap. And actually, I think that in some instances, some of your questions might get answered as you're with us for the duration of the day. And so that takes care of all the sort of mechanics. If you like what you see, a selfless plug for the focused remediation seminars. We've got a few events coming up in September 5th, November the 7th, December the 12th. That's going to cap off the 2024 season. That will make, I believe, 7 events in total that we have done in 2024. We've gone to a much more exclusive and limited calendar. We've got a lot of attendance at those events. If you like what you hear, if you like what you've heard previously, please tell your colleagues, spread the word. You can get onto that website, Focus Remediation Seminars, and register for those upcoming events. And typically, we have secured PDHs and CEUs for those events as well. That brings us to the story, right? And what's the story? So those of you who may not know me by trade, but I spent 22 years as a potential responsible party rep and managed a portfolio of environmental liabilities for an old line chemical manufacturing company that was headquartered here in Pittsburgh. And for part of that time, I managed basically the groundwater portfolio and how we addressed our sites. And we had that unfortunate release scenario at all of our facilities. We were old line, primitive manufacturing techniques, really didn't care too much about saving the volume of material because the throughput was literally in millions of gallons. And so if we missed a few 100,000 over the course of a few decades or more, we really weren't too concerned about it. The way we measured product was in massive tanks with floating balls that went up and down. So if we lost 1% or 2%. Maybe we don't even know that in the math. But at the end of the day, I wasn't there when all that was going on. I was just there to help us fix it and drive the remediation of those sites. And when I stumbled into these guys and this technology, recognizing some of the attributes that you're going to hear about today, it immediately piqued my interest, not so much for what I'm currently doing today, but as a guy who was out there chartered with trying to find solutions for sites, this would have been the answer. And I am particularly intrigued by the cost. And because the environmental industry is so cost-driven, the return on investment is such an imperative calculation in what we do. When you hear about what we're doing today and what these guys are presenting, you're going to understand and see what I see as certainly the wave. And I put up this slide in case you guys missed it. This is Kristen Faulkner on Saturday, and this is women's road cycling. I don't know if any of you caught this, a super exciting race for basically almost 4 hours. She rode in 4th or 5th place behind the leaders who were about 30 seconds out in front of her. And she managed to creep back up in the last half hour of the race to put herself in position where she could actually see the leaders. And as she crossed the Seine River in classic form, she uses the momentum around a big turn and swings it and just makes an attack and just goes for it, right? And she drops the leader and the 2nd and 3rd place person. They couldn't hang, right? And that's what I see coming out of this technology, to be honest with you. I see these guys are right in the catbird seat to make that attack, right? Swing themselves into position. She rides down under the Eiffel Tower, crosses over the Seine River, holds her bike up. She wins a gold medal out of nowhere. In fact, she actually won another medal in women's team indoor cycling this week. This happened on Saturday. She rode in 2 different events, which I thought was super impressive. But I believe that these guys are in position perfectly to make the attack. Right? They are going to be a force to be reckoned with. When you see what I saw, and if you sat where I sat and recognize the kind of attributes that this technology has, and it really gets down to cost, right? These guys are providing a continuous oxidant stream into the groundwater for less than $6 a day. And I used to manage up to 17 wastewater treatment plants where we were trying to treat the water that we are generating for remediation sites, and I can tell you, that $6 a day was nothing, right? Yeah, it's 2 coffees, that's 2 Starbucks, exactly, right? So obviously there's a capital cost involved, but running these systems for long term, there are sites where this stuff is the answer. We visited, the technology is imported to this country from Israel. I'm sure these guys are going to talk about that. We went and visited some of the sites where they were working on. We met the inventors from this, and they came at it from such a whole different bend. It was interesting to hear why they were getting there. It really came from an angle of trying to be guys who were trying to protect corrosion of underground piping and come up with a technology that could do that. But, oh, by the way, it also solve their environmental problems and releases at filling stations. So I think you guys are going to hear a great story today. When all these pieces come together, it's going to be very interesting material. And so I want to say thank you again to all the folks who are joining us, both virtually and here in person. We owe you lunch out there or a beer or something for sure. And and one last thing, consistent with what we do for our focused remediation seminars, for every person who is out there, the sponsors for today, Provectus and Field Data Solutions and Field Environmental have agreed, if you stick it out and you stick with us for the whole day and you get your accreditation, we're going to add $1 for each participant. If you ask a question We're going to bonus you guys for make that $2. So if you ask a question today, you're going to generate $2 for a good charity. We've done this as part of our program. I think we've contributed almost $50,000 now over the years to philanthropic organizations that support geologic sciences students out there in the real world and bringing them around. So with that, I am going to turn it over to our first speaker. I'm going to turn it over to Troy, whose mission is to explain this technology for you. Troy, why don't you come up out of the audience, and we'll get you going, buddy.
You good? Good. Appreciate it. Mitch, thank you very much. We appreciate the opportunity to come to your facility. I'd like to thank everyone that's joining us here in person as well as those that are joining online. Gives us the opportunity to reach, obviously, a large audience rather than just here in the Western Pennsylvania region. Unlike Mitch, I hate being tied to a lectern, so I'll be off here more to the side.
Assuming you can get your slides to
work. Right?
Yeah.
We're having the same issue with the slide advancer. My portion of the presentation today focuses on the modernized approach to ISCO by eliminating the need for chemicals. That's the general premise of what we're looking to do today. Brief outline on the presentation. Give you a real brief introduction to Provectus Environmental as a company. I'll go through the Provect-EBR technology and specific case study information. And after John's portion, we will have the live demo out with the equipment that we have staged here at the facility. And then we'll do a question and answer. Again, as Mitch discussed, the chat tab is there. If you have questions as we're going through those, please feel free to click on that, enter in your question, and we'll be ready to go. And you can also, if you'd like, you could go to the questions and answer. They're just telling me the Q&A is a better option than the chat. So if you do have a question, please click on the Q&A tab and type your question in there rather than the chat. That way we can record and maintain those questions. So a little background on Provectus. We've completed probably well over 2,000 remediation projects, both here domestically as well as internationally. Our backgrounds are in consulting, remedial contracting, development of advanced remedial technologies, and also injection and drilling work as well. The company was started in May of 2014, and it was through acquisition and utilization of specific patents in both in situ chemical reduction, in situ chemical oxidation, and methane inhibition. Provectus is a technology provider. We are not in-field implementation. If turnkey projects are required, we partner with other companies throughout the U.S. as well as global. If complete turnkey design is required, we can do that as well. So I always like to put this slide up. This is kind of one of those guidelines that I use. I always like to work with my subsurface conditions. I'm not one to try to push a rock uphill. So we like to gather as much information as we can on our site chemistry, geochemistry, the lithology, and get a determination of what is the proper technology to apply. So you can see various Provectus technologies at each, specifically looking here at ORP. The one thing that you'll see, the Provect-EBR on the far right-hand side of the screen shows this technology really covers all of those conditions. So we can apply this technology really across the board, and we'll go through how we achieve those means. So why do we need a new technology? First, looking at in situ chemical oxidation. I'm a huge ISCO fan. To me, that's my big hammer to go in subsurface and attack large mass of contaminants. But there are issues. The longevity of the oxidants that we put in, the most reactive of those are those reactive oxygen species or those radicals. Very, very reactive, but also very short life. So we either have to continually regenerate those or introduce new chemicals. PRBs, we certainly like to do that. Normally that's done through reductive technologies, not through chemical oxidation because of the short lifespan of chemical oxidants. We tried things like the cylinders or candles where you had wax impregnated oxidants using potassium-based oxidants for that extended release due to reductions in solubility. Those help, but they have their limitations that, those are effective for maybe 3 to 4 months. Typically with a PRB, if we're doing a true PRB, we're looking for 5, 8, 10 years of activity within the system, from the system. And all of those, not being able to be effective in, with specific contaminants. Deep aquifers, certainly we're going to have a major challenge trying to set up treatment or PRBs in deep aquifers. And certain lithologies, the tight silts and clays, fractured rock, karst, those type of environments are a major challenge for your traditional in situ chemical oxidation methods. So, and again here, one thing that I always like to look at is when we look at our options from a chemical oxidation standpoint, this oxidation potential kind of gives us a rating of which ones are more reactive as we go through. Permanganate's kind of down there toward the bottom at 1.68 volts. Then you get up higher. You get up to the radical species, the hydroxyls and the persulfate radicals. Now we have those species that are very reactive and can treat a wider range of contaminants compared to those down below. So why is this technology important? This is actually a business in my hometown in Ohio that's actually a demolition company. And this small excavator sits right out in front of their facility. And I've carried this with me for a long time. You can't do today's job with yesterday's equipment if you want to be in business tomorrow. So you kind of see down there at the bottom, that's kind of what I call yesterday's equipment. We've done the same things for so long, same type of equipment, same type of approach. You reach that limiting factor. So we need to find a better, more advanced way to push this forward beyond what we can do today. So with that, we introduced 2 years ago the Provect-EBR technology here in the United States. As Mitch mentioned, this technology was actually developed in Israel. My colleague Jim Mueller was actually traveling that area and presenting on traditional Provectus technologies. And within Israel, as he's talking to folks, kept getting the feedback, we don't do chemicals, we use the EBR technology. We use EBR technology. And you hear that often enough and you kind of think to yourself like Jim did, hey, I need to go check this out. So he went and met with the folks that developed and marketed the technology, the inventors of it, and we formed a relationship and partnership with them. And the general, what I call my three elevator floor explanation of the technology is we are creating elemental oxygen and then converting that to hydrogen peroxide, all in the presence of a ferrous iron release. And if you know, when we get that ferrous iron with hydrogen peroxide, we're going to generate Fenton's chemistry in those very, very reactive oxygen species. What you see here are the primary components of the system. The photo on the left is a snapshot of the portion of the control panel. Once we get outside into the bay where we've deployed the trailer, we'll go through the entire system and see each of the components and what they do. The photo down here on the lower right are the two downhole components of the system. And actually I've got one of each of those with me here today. This is the EBR reactor that we generate in there down into the well. Typically, we're deploying these in 4-inch screen PVC wells to whatever depth we're looking to treat. And the second component is our sacrificial iron electrode. And you can see that in the picture on the lower left in the background, that's the electrode. You can kind of see that it has already started corroded. This is actually one as it's brand new and hasn't been deployed. So it's nice, shiny, before we are passing specific current through it to accelerate the corrosion and release of those iron particles. The other component to this is kind of demonstrated in the photo in the upper right. That's our control panel. One of the very unique things about this technology is we are able to monitor and make any necessary adjustments to the technology remotely. We do that with our partnership with Field Data. Using their platform, we can connect to this through cellular connection anywhere that we can get decent signal. And also, we've also started talking about potentially having a Wi-Fi connection as well so that we can access this. I can monitor the performance and make any adjustments we need to as the system goes. That eliminates the need of having to travel to wherever the system is deployed at. I can do this anywhere that I have an internet connection. We can access this and track it, which really makes it unique within our market. This is a patented technology from the Algresi Group. The Algresi Group is based in Netanya, Israel. It's patented both here in the United States as well as in Europe. Again, we've got a partnership with the Algresi Group to be the provider for this technology in North America, Europe, and in Southeast Asia. They support our efforts both from an application and technology standpoint, and we greatly appreciate the help that the Algresis have given us as we've moved this technology here into the States. So this is, and after Doug's presentation, this is one of the original slides that we generated on the technology. So what we're able to do here is address all of those challenges that we outlined earlier with traditional ISCO technologies. We can attack deep aquifers. The reactors and electrodes really don't care. They don't know if they're 15 feet below surface or they're 150 feet below surface. It's going to perform and react regardless of that depth. So we can attack that. Looking at those places where, and we've seen it, where just throwing carbon at it where you want to do absorption or sequestration, if that's not considered an effective response, if you actually want to treat something rather than just holding and condensing it, this is certainly a much better technology to go to. And then alternatives to hydraulic containment or the pump and treat, which typically have, I've always termed those as retirement projects. You start that project the day you start working and it's still running the day you retire. So you get those, long-term O&M costs that we're able to avoid. So the one thing that we said is the technology's really effective across the wide spread of contaminant mass range or concentrations. We show this going all the way out, to like 50 milligrams per liter. Once Doug has an opportunity to present on our most recent deployment of the system, that number's got to push way far to the left. It's pretty incredible what we were able to do at Doug's site, and I'm not stealing his thunder for sure, but it will be interesting to see. So how the system works, again, when we looked at the EBR reactor that's deployed in it, the photo there on the right-hand side is actually the EBR reactor in a tank of water. This is a photo that I took, as Mitch mentioned. He and I was able to travel with the team over to Israel. This is actually at Algresi's headquarters in Netanya, Israel. They're running the reactor in a tank of water. You can see the effervescence there. That's that generation of elemental oxygen. So we're taking on the catalytic surface of the reactor, we're converting water, and in a deployment stance, this would be groundwater. So these components need to be exposed in groundwater continuously. So it's taking that groundwater and converting it through electrolytic reduction to elemental oxygen. And then on a cathodic surface, we're doing a 2-electron reduction of that oxygen into hydrogen peroxide. And again, we've got that sacrificial iron electrode that sits below the reactor that we're forcing a specific current through it to accelerate that corrosion and release of iron particle. Again, generating that Fenton's type chemistry with the hydroperoxyl anions, the superoxide radicals, and the hydroxyl radicals. Depending on our subsurface geochemistry conditions, we may also be generating ferrates. The chemistry portion of the presentation is there on the lower right-hand side. We start generating these self-propagating reactions as these materials move outward radially from each of our EBR locations. So you can see there how we go with the oxygen and convert that to hydrogen peroxide, its interaction with the iron 2, generating the radicals, and we also get to an equilibrium point of, it's similar, it's a Haber-Weiss reaction where that iron 2 and iron 3 share that electron back and forth. So we get this repropagation of these reactions radially outward from each of our EBR reactors. So how, if you're familiar, if you've ever seen, studied electro-Fenton's generation, you may think, well, hey, this is the same thing as an EF generator. The differentiation here is the production of these iron +2 and iron +3 nanoclusters that we set up this redox front through thermodynamic differentials. We literally create a outward propagating redox front, truly radial from each of these points. This is not dependent on groundwater flow direction. We truly see a real radius of influence from each of these points. And as we do that through these generation of Fermi level energies, and we have the ability to dynamically couple multiple reactors that are deployed in the system, and how we have the multiple different reactors set up and working in conjunction. If you use a, what do we call it, when the nodes in your, a mesh network, a Wi-Fi mesh network at your house, where you've got those pods all over your house and each one of them generates and they start to mesh together. We see this similar thing with this EBR reactor and one next to it. As though those wavefronts propagate outward, we start to mesh together and then can treat a greater area than a single reactor will on its own. So when we look at those iron 2, iron 3 nanoclusters, you know, again, this is a critical part of it in, you know, generating that thermodynamic differential with these Fermi level wavefronts. And it's that shuttling of that electron between those iron 2 and iron 3 particles at the types of ORPs that we're able to generate here. That's the driver for implementing that radial flow, that radial front from each of those points. Where if you're familiar with an EF generator, an electro-Fenton's generator can do that, but you have to be in direct contact with that EF generator. It does not propagate out radially. And that's, you know, one of the differentiations here. And we've seen that in our field implementation, taking our monitoring data at specific distances from each of these points. You can see that change in both time and distance. So we're able to, as the system runs, we can predict we're going to get to this distance and this distance. Typically, we see the ability to reach out to between about 18 and 22 feet radially from each one of our points. And the benefit here, it's independent of our lithology type. So those difficult lithologies, the fractured rock, the tight clays that are problematic for those other technologies, these actually work extremely well. So what we're able to do with the system, from a deployment standpoint, we can do this as either a fixed deployment or a mobile deployment. The photo on the far left is actually a fixed deployment at one of the sites that Mitch and I were able to see when we were in Israel. This is at a fueling station actually in Netanya, where they have it deployed right beside the gas station. It just looks like any other electrical panel. All of the components are wired through that cement pad that it sits on, and everything goes through channels. They've trenched it in and concreted everything. Everything runs subsurface. When we brought it here, the first thing we wanted to do was make this thing mobile. So we took the control panel like you see on the left-hand side, and we made it larger. So this system can run up to 10 reactor electrode pairs, and put it into a 16-foot trailer. So we can not only take it to different sites, and this is what we term our pilot or proof of concept unit. So I can take it to a site, deploy it for a determined period of time, prove that the technology works and is effective, and once that's done, the client would make the decision on moving forward and putting a permanent full-time system, and we can move it to the next location. The other thing that we can do at larger sites, we can treat a specific area for a given amount of time, and then since it's mobile, move it 100 feet, quarter mile, a mile, whatever we need to do at that specific site, and move it to a different location. So that's a picture of our trailer. The photo there on the bottom on the right, that's our most recent site that Doug's going to talk about. This was right after we moved from our phase 1 to phase 2, and we redeployed all of our reactors and electrodes. I'm actually on the phone through WhatsApp with my colleagues in Israel, with Gil El-Gressi in Israel, and we're doing all of our calibrations before we restart phase 2. So we can probably within a half hour's time move it from one location to the next and have it up and running. So again, quick summary of the technology in its probably most basic form is that generation of hydrogen peroxide through conversion of elemental oxygen over to hydrogen peroxide, in that release of iron that we're doing with the iron electrodes, again, to generate those reactive oxygen species, and through those propagation reactions continually to generate those reactive species moving outward. And the one thing that we do, once the system shuts down and we go to another site or move it off site, we transition from an ISCO to a bioremediation, utilizing that oxygen and iron that we leave behind as electron acceptors. So we kind of see it transition into a biotreatment, polishing long term if that's what's required. And again, the really cool thing with this is everything's monitored, controlled, and adjusted remotely through our use of the field data platform that the system is connected through. Where's this been used? 2021, Israel had 35 gas stations under active remediation. That may not seem like a whole lot unless you've been watching the news lately and you gather the fact that Israel has the landmass of about the state of Vermont. So it's not a large landmass. They had 35 active gas stations undergoing remediation. 14 of those were being treated with the EBR technology, as well as 2 chlorinated solvent sites. At this point, 7 or half of those sites are in clean closure monitoring after 1 year of operation of the system. It's ISO certified and actually approved by the Israeli Water Authority, which would be equivalent to like our EPA. If you have a fuel station or anything with fuel releases that are impacting groundwater, the Israeli Water Authority is recommending that this is the method you use for treatment. We had performed here in the United States a PRB deployment pilot operation at a industrial landfill, and we have the pilot test that we ran on benzene release for soil and groundwater that Doug will cover in detail in his presentation. So a couple quick case studies that I want to go through separate from Doug's presentation. This is one of the solvent sites that they did in Israel. This was deployment of a single EBR reactor in that W6A well. You can see, our depth of water here is at about 20 meters, so fairly deep impact. Not, fairly typical for that area. It's a sandy aquifer. PCE at about 257 ppb. TCE obviously was our driver at about 25,000 ppb or 25 ppm. The reason I put the data up here, not only to show that the system is effective in releasing that material radially, but also to show that it's effective both up gradient and down gradient from the site. The well 6 is 10 meters up gradient of groundwater flow from well 6A where the EBR system was deployed. And you can see, obviously our TC contamination wasn't as high 10 meters away as it was a really localized release. But even 10 meters up gradient as well as 20 meters down gradient, you see within 60 days, that's 60-day sampling, certainly able to take care of chlorinated solvents in very rapid fashion. The second case study, this is the Negev Zednik site in Israel. This is an active and operating fueling station. This is actually one of the ones that we were able to observe while we were there. Mitch, if you recall the deployment, we were standing about right there by the station taking all of our pictures. This is a system, they deployed 5 of the EBR reactor electrode pairs. Again, here groundwater's a lot shallower than the last one, here at about 7 to 8 meters below surface. Again, typical lithology here, sandy aquifer with silicon clay lenses strewn throughout. Fairly standard when you're looking at a fuel station release. Our contaminants being MTBE and TPHs. You see we're greater than 50 milligram per liter MTBE and more than 100 milligram per liter of TPH. Not a huge site, which we would expect for a fueling station, about 240 square meters in total treatment area. This is, I always like to bring this data up as we discussed earlier when we're generating those Fermi level wavefronts. A lot of it is, that's ORP driven as we're able to generate these high ORPs. You can see fairly standard for this type of site, somewhat reducing conditions to begin with, between about -150 to -200 ORP. You see that point where the EBR system was started, and in rapid fashion you see, ORPs. We're seeing about a 900 to 950 unit swing in that ORP in short order once the system was operated and sustained for about a year and a half's time. Treatment data from that, you see again, TPH as being a concern. Here you see the various depths that samples were taken, anywhere from 1.5 meters below surface down to 7 meters before and after in area A, this upper area with the TPH. Same thing in area B, which was located right between 2 fuel islands. And area C was an area that bordered the station set right on a corner. So those were the 3 areas of concern. And you can see in that amount of time, this ran for about 18 months, continuous operation. Goals here for this, they wanted to see reductions. They were hoping to get from that 100 ppm down to 400 ppb, and the system was able to get it to below 5 ppb. So certainly effective with the fuel components as well. When you look, you see a similar thing with the MTBE. Again, baseline contamination at about 50 ppm. Their goal was, goals and aspirations were to get to about 1,600 ppb, and the system was able to get it below 50 ppb in that amount of time in operation. Again, these are a couple pictures that you'll see here. Again, this is the actual trailer we have here on site today. And once the second presenter, once Doug's finished, or once John's finished with his presentation, before Doug goes on, we're going to go out and do a walkthrough of the trailer, see what the components are. And we actually have one of the reactors currently running in a display tube to simulate one of our well applications, and you can see the reactor in operation. But again, this allows us to really take this system anywhere in the country. So that's my portion of the presentation. I appreciate everybody being there. We're going to transfer over to John, who's going to be here remotely.
Troy, awesome. Thank you. Appreciate that, man. And I can tell you that that small footprint gas station, when we walked up onto the gas station, we're kind of looking around like, where is it? Like, it's a busy gas station, as you can imagine, in a very urban area. And that photograph that he showed, there's the men's room and the ladies' room, and then there was the EBR in a closet that just was tucked away back there. And if you hadn't known what you were looking for or could see the trenching, the operation of that facility was just rocking and rolling. Place was a buzz. In fact, you had to be careful not to get run over by a car. People kept looking at us like we were there to like wash windows or something, do oil checks. But at the end of the day, it was a valuable experience because we could see how little impact it was having on this facility's operation as well, which for a filling station. So we're going to now switch to a virtual presenter. John Wright, my colleague from Field Data Solutions, is joining us live from Reno, Nevada. John has been intimately involved, was on our trip to Israel with us. John, we're going to kick it over to you and have at it, man. We're running just a few minutes behind time, so take the time that you need, and thank you.
Absolutely. Thank you, Mitchell. Excellent presentation, Troy. It's always hard to follow up with your presentation. As Mitchell mentioned, I'm John Wright. I'm with Field Data Solutions, originally from Pittsburgh, at the main office there, born and raised, and recently, a few years ago, moved to Reno, Nevada. So greetings from the Pacific time zone. All good. Can you guys
to get started again? John?
Yeah, can you hear me? Mitchell, can you hear me?
Can you hear us?
Yes.
Yes, you can hear us. You are on
I can
mute.
hear you. You cannot hear me?
You.
Okay,
you
let me try.
Though. I can read your lips. Thank you.
How about now?
Try to get John squared away.
Do you have audio now?
And I'm sure we've tested that connection beforehand. Well, we did say that this was going to be live TV. Yeah.
They said they can hear him.
Oh, perfect.
We're the only ones that can't.
Okay.
Mitchell, do you have me now?
We can't hear him.
Yeah, I guess turn the volume on.
Sorry, that's us.
Yeah, sorry.
Okay.
We were worried about that. Okay, we've got it confirmed. John, why don't you start over for everybody, and we're good to go, buddy.
Okay, so I am online as far as the audience, correct? I'll take that as yes. As Mitchell mentioned, I'm based out of Reno, Nevada at this point. Privileged to work with the team, and this is kind of a cool way to do it remotely since we are talking about remote data. As Troy and Mitchell both mentioned, I've been involved with Provectus and FDS integration of this technology and the implementation on a few pilot projects here in the United States. And I'm going to focus on my presentation on showing you some of the real-time aspects of the control to the system, as well as performance monitoring related to the EBR technology. Can I get a thumbs up out there? Maybe Mike on Teams that you can hear me? Or somebody in the audience? Okay, cool. Thank you, Michael. Appreciate it. So what does FDS Field Data Solutions do in support of the EBR technology? Well, we have a close involvement with the team overall, with Provectus as the vendor, with their clients in the planning, the operation planning, as well as the maintenance and monitoring program that's put forth for the pilot study or for the full-scale application. We provide the system communication, the cellular modem, the data packages, things like that, to control the trailer that Troy is going to show you during the break and get that data from the trailer and the site up to the servers for the team in general to be able to collaborate and make decisions and control the system. We integrate that controller data onto our real-time platform called FDS Connect, which I'm going to show you some screenshots from. We then add on performance monitoring. So the two aspects of our involvement are, number one, the control of the system, and then the second and separate is the actual performance monitoring of the effectiveness of the actual EBR technology. And as I mentioned, we facilitate that interaction on our website between, in this case, Provectus, the technology developer in Israel, the client or clients, stakeholders, and other people involved with the project. And that, again, is a worldwide collaboration. Me being Pacific time, Troy Eastern right now, and our support with Algresse being in Israel. And just this morning, we're trading back and forth communication. FDS also provides an element of field services support with deployment, maintenance, things like that as well. Mitchell there in Pittsburgh, the owner of the company, will probably touch on that directly with participants in Pittsburgh during the trailer walkthrough, but we have that element as well. So as Troy mentioned with the EBR system, and I just wanted to kind of seg from his, the signal path above ground, below ground, above ground. We've got the EBR well itself, as he mentioned, is a reactor and electrode combination, as well as an air tube for an air supply at the bottom of the well. So that's shown there and highlighted on the far left. The trailer in this case, as Troy mentioned, is a mobile environment, but whether it's a fixed control panel system or a trailer, we've got the trailer with the control modules and modem. And then we have, as I mentioned, a performance monitoring aspect. So in this case, between the EBR wells, we have piezometers and monitoring wells that are where we have water quality sondes and real-time data instrumentation shown in that gray box, where we're getting that data from the same site. So in an overall map view of that same site, you can see here where we have, in this case, 3 green EBR wells. So those are the 4-inch wells with Troy Provectus equipment in it. Then we have a combination of piezometers, the 2 red ones, and 3 monitoring wells located in the triangle around the system. And again, this was for a pilot project. In this slide I'm showing you here, the active EBR controller in a well, in a simulated well, going down through that saturated zone. As Troy mentioned with his slides, on the left we have a clean reactor with those plates, and you can see that in the blue well in the video. It's the upper component. And then on the right, we're showing you some sacrificial iron electrodes, and then the air pump system that's in this case located in the Provectus trailer that has air tubes going down to the bottom of the electrodes. And you can see here, I'm kind of moving my cursor, that black tube at the bottom is the pre-tubed section of air line. So that pump is delivering air to the bottom, sparging it up through that system. So those devices then in the wells are then with their electrical wiring pulled up through the top of the well into the control trailer that is out in the bay at FEI right now. Those wires come in, showing you on the far left there, where they come into a series of breakers and terminal positions. They go in through a series of electrical components that are located in the control trailer. Those components are connected to individual modules, which Algresse has designed to control the electrical parts of the system. And the multiple modules are then continue the data flow to one central controller per system. So in the trailer in the bay, we have multiple modules that can hold up to 10, support up to 10 EBR wells, and those all go into one single controller. That controller then communicates through a cellular modem in the trailer, and then it goes up to the servers for Algresse, Provectus, FDS, and the team to be able to see that data. And then that data is a two-way communication stream so that the programmers, mostly Algresse and Provectus, involved in making operational decisions, can then reprogram and tweak and adjust the modules to then affect the EBR system performance. So it's really an optimization and a two-way communication stream there. You might be able to see there during the video some of the dials that are moving back and forth on voltage and amperage. So what does that all mean? It all leads up to a very complex but digestible page. So this is a screenshot. I'm going to take you to a live demonstration, but this is a screenshot showing a 4 EBR well, and the 4 EBR wells are at the bottom, showing some amperages and voltages of various types. And up on the top are a series of 8 performance monitoring wells. So in one web page, our clients are able to see the operational aspects of the EBR system, as well as performance, radius of influence, things like that, in the performance monitoring wells. This is the live demonstration showing you a site actively in Israel, the one site actually that Troy had mentioned, showing you our web interface, where we have a full GIS platform showing you status, position and status of monitoring wells and EBR wells. We're showing you each operational status of, in this case, it's an EBR well 1, where I'm changing it from a reading to a 10-minute average. So now you're seeing things like the voltage and amperage. And again, this is operational aspect. So this is what Provectus and Algresse are looking at on a daily basis, a real-time basis, on a trend basis, to make decisions on if the EBR reactors are performing as expected, to make adjustments for optimization, and then in long term, to see if things like maintenance is required, or troubleshooting is required, or positional changes are required, things like that. And when Troy does the walkthrough of the trailer, he'll show you some of the stuff as far as components in operation. This is a screenshot of that live web UI, but what I wanted to point out here in particular is on the, sorry, let me go back to that. Clicked a little too quick. On this far side of the graph, where the reactor amperage, which is the light blue teal line, is fairly consistent, and this was for weeks. And on this particular day, it started to decrease. So we have alerts and alarms with text and email. So Troy was able to get an alert saying the amperage went from what it was positionally about 8, and it dropped below that, so that he could jump online and see it, and then communicate with Algresse and see if there was either an operational issue or something going on that needed attention related to that particular reactor. And then this video clip is going to show you a morphing between different wells of some of that kind of operational data. So on a daily basis, you, your client, technical director, interested party can get into the operational aspect of this and see those trends. You can see right there where these are nice, clean peaks, consistent, things like that. So we're looking for trends of changes in these kind of control parameters. Just to kind of, again, reiterate some of Troy's pictures, but show you in the context of real-time data. On the left, we have a new reactor that went in. You can see there in the middle picture how after a period of deployment, some scaling at this particular site started to occur on the reactor plates. And on the far right is just a little bit of scaling and some iron looking deposit at the top of the picture, if you can see that. So what this is showing you is real time on the web interface. As the reactor was in place, that scaling in this case actually led to some changes in amperage and voltage. So again, operationally down in the weeds, Provectus and Algresse together could make decisions on perhaps it was time for routine cleaning to occur on site. And they could optimize the amount of site presence and trips needed to the site. Troy may speak to that during our Q&A portion, but that's what the real-time data for the operational aspect is giving the team, this kind of knowledge. Here again, these are brand new electrodes. They're sacrificial, so they are to degrade and produce that iron that Troy was mentioning. But you can see how in this picture in the middle and on the far right, how quickly that sacrificial iron really did its job. But as that would degrade, and you can see on the very far right, quite significantly, the changes in those operational parameters, the voltage and amperages changed on the live data. So you're able to see that and then know to optimize that trip out there to replace that sacrificial iron, perhaps every 3 weeks. But when you notice the change, the trend may change and it might be quicker. Now you have to make that trip every 2 weeks or maybe widen it out. So you're able to make those decisions and optimize your efforts in real time. The other aspect, as I mentioned, is performance monitoring. So in addition to the operational things I just showed you, we are doing some support with this statement here, effective ROI, where you can validate that real time and see the effectiveness and the efficiency and the overall radius of influence on that system, especially in pilot studies, but also applicable on obviously in real-time full-scale remediation applications. So in this case, this table shows you some of those parameters that we're all familiar with, where you're measuring DO, ORP, turbidity, pH, conductivity in real time. The sondes that we deploy are also giving us things like barometric pressure up on surface, as well as depth of the sonde is deployed. So we're measuring those parameters in real time, showing that perhaps 8 feet out from the EBR well, that the ORP is trending in a way that the Provectus and Elgrese expect it to trend at a certain period of time. This is not, just to point out, benzene-specific performance monitoring. So what we're monitoring here are key parameters that the team knows and understands are indicators to the effectiveness of the technology. Specifically ORP, conductivity we found is important. Things like turbidity, less so, because obviously we're bubbling air with iron in it, so we are generating high turbidity. So we found that turbidity is not as critical as a secondary parameter. DO, obviously we're also interjecting air, so it should be high, but the DO can be important real time to be an indicator that the pump system and tubing system is working as expected. So some of our typical monitoring points, we as FEI and FDS support a variety of manufacturers in sondes and sensors. In this case, it's an aquaread sensor that we deployed on the last pilot study with multiple sensors installed on the sonde body, as you can see there. This is an FDS communication box with our modem on the opened picture there on the far right. As you can see, a very small footprint, little 8-inch square box just put right on the well stick up. We communicate real time through our modems. We can go solar, DC power, AC power. In this case, we actually were using AC power from the trailer, but depending on the size and application, we have multiple ways to implement this. To show you some of the data coming from the performance monitoring. So again, we have operational data and charts showing the performance of the system, and now we're showing some of the water quality data coming from the performance monitoring. In this case, this was a piezometer located in very close proximity to one of the EBR wells. I believe it was about 8 feet away. And what I've highlighted in the circle, you can see a very dramatic change in ORP from negative 129, 120s to positive 600s. This is what Troy and the team are looking for, and you can see this is actually very dramatic. So after weeks and weeks of the system being in initial operation and at the baseline water quality chemistry of the formation, we see this trend, and we saw this in one day, where that breakthrough of the EBR system actually got to this position at this well at that depth. And so again, we have alerts in place. So we all were pretty excited that day where we had an ORP alert that went above 0 or 100, whatever those tiers are. we all jump online, look at it, and we can see that this trend was occurring. And then we can also see the other wells and see what's happening up gradient and down gradient. But this points out the availability of this data to the team worldwide. Another example from a different well, I was just showing you kind of similar trend, different application, but we're not as dramatic, negative 109 up to the 119, 120 range. But this also shows you where we had a specific period on purpose of a data outage, showing you that small little gap over on the midsection. But again, just showing you some utility where the team worldwide can get on here and see what's happening with the system itself, in addition to the operation with the performance. So with the pilot testing that we did, again, as a team with Provectus, El Gresse, Doug is going to speak to this on his pilot through AECOM at some of the sites. We located our sondes inside of the actual EBR wells, literally on top of the reactor system. Not a great idea as far as the electrochemical reactions that are going on there. We learned a few valuable lessons to how reactive that environment is directly in the well. But we wanted to see what was happening with ORP and some of the parameters directly in the well. We also located sondes at points between the EBR wells, as I showed you on some of the maps. We located sondes in the perimeter, up and down gradient, in combinations of all three of these as well. We've also discussed as a team the pilot use of above ground flow through cell style, where we're actually going to bring the water up through tubing and in Troy's trailer. And when you do the walkthrough, he may speak to the availability of the real estate within the trailer to do this, where we might set up a bench and actually get above ground flow through. We've evaluated the data from the primary, like ORP, and secondary, like conductivity for the water quality parameters to see their usefulness and the cost effectiveness of doing real time versus things like grab samples and lab samples and field measurements. And then this all, as I mentioned, leads to the team discussions, both real time and maybe weekly or monthly, on the benefits of the real time monitoring and how it relates to the performance of the system overall. A typical, this slide's a little bit wordy, but what I consider typical and expected, since we are in a pilot study phase of implementation with Provectus, where we've done this at a few sites, we've learned a few things, like baseline pre-EBR energization. So before Troy gets there with the trailer, or while it's being set up, getting that day or week of baseline data online through the sondes, not necessarily repetitive to your laboratory samples that you probably have from a site, but true pre-energization samples. And then we have the time when Provectus initially turns on the trailer. There's an initial 1 day, 1 week, multiple weeks where that system is getting energized and starting to do its job underground, where we want to gather that data in the real-time aspect. In the close data points are pretty important at that point, as we're learning when that breakthrough may happen, since it's an unknown point of time. And then we see that first EBR breakthrough. That's what's expected. That's what we want to see. That documentation is pretty important, real time. And then at that point, what we've learned is after a breakthrough, we're really in this sustaining phase. So these have been pilot studies with a fairly short duration, but perhaps the site's going to go on for 6 months or 12 months as planned. So during that next phase of that long period, we're in this routine operational phase of EBR. The aspect of the controller system is very important because the team needs to know how those reactors are reacting as far as amperage and voltage in real time, consistently 24/7. You're looking for things like drops in those amperages and voltages, indicating that scaling or the corrosive effect on those reactors. The performance monitoring, you could go to a less often, pinging the sondes less often, things like that, just from an overall implementation. And that's where we are in the adjustment and the cost effectiveness of how you implement these two together. Then there's the EBR pre-shutdown. You know you're at the end of your 12 months. You're going to shut it down. So getting real time for that next couple days and knowing what's happening is important. And then you're in your post EBR or post remediation phase that we're all probably familiar with your long-term monitoring. You could keep some of the performance monitoring in place for a period of time to see the rebound effect. And I did also want to mention, it's a little out of place in this slide, but there are other data inputs, such as the last pilot we did, the utility company had a smart meter providing AC power to the trailer at the trailer drop. And that meter with that utility company, like most of us are familiar with at our homes, you can usually get that data real time or daily. And a lot of times we could get that data through the utility company to add to the web interface as part of our data set. So some of the key points to take away is that cost-effective control aspect of monitoring the EBR operation in real time and how that would save on everything like visiting the site, visiting the trailer every day, looking at the operational aspect, pulling components out of the ground when they're healthy and they don't need to come out, things like that. The team knowledge and collaboration of that system ops, the optimization of those maintenance and troubleshooting activities, and then the real-time knowledge of the actual impact of the remediation. Is the system performing and affecting the groundwater chemistry as expected as you're progressing through your pilot or full-scale remediation? So in a nutshell, that's it. I really appreciate the time joining you from Reno. Wish I could be there for lunch. Maybe you had pierogies there on the East Coast. But that's it for me. We're going to do a Q&A, I understand, at the end of Doug's presentation. So we'll queue up the questions at that point. So Mitchell, back to you.
Is that good? I can hear it actually. Perfect. All right, here we go. Well, welcome back to Pittsburgh. As I mentioned, we are broadcasting live. This has been unrehearsed and unscheduled, so we appreciate adapting to our production schedule. So what we're going to do is follow me, and we're going to go out to visit the actual technology that we've been talking about. So come on, walk this way, and as we go, we're walking out into the Field Environmental Instruments warehouse. Thanks for joining us. And as you can see, the folks over here, we actually had lunch today. And not only did the people who came to visit have lunch with us, but our employees were treated to lunch on your behalf. So a big thank you to all of those for doing that. At some time, I'd love to give you a tour of the warehouse. So if you ever get to Pittsburgh and you want to come visit us, or you're living in Pittsburgh and still looking remotely, just ring us up. We'd love to have you at the facility and show you around some of the things that we're doing here. So follow me. Here we go. We're walking over towards our bays where we do our equipment. This is the water quality equipment. John just got finished talking about the setup that we had, and we've set up a little demo. If you come over here, this is the AP 2000 that John was talking about. It's got it connected up to its gateway for live transmission of the data. And in fact, when we get into the tour down there, we're actually going to move this equipment down there and test it out for you. This is a self-righteous plug for Field Environmental and Field Data Solutions. We set this up because we knew we were going to be walking by here today. And watch your step, Zion, as we're moving down here. Some of our equipment that we deploy out in the field. This is our craft here at Field Data Solutions and Field Environmental Instruments. These are air monitoring stations. If you've seen some of our work, this is a very commonly deployed piece of integrated technology that we offer. And so now we're headed down here out to the truck bay. And come on, Zion, follow along. This is the trailer down here. And watch your steps, okay? Here you go. First step, second, third, fourth, fifth. Actually, you're on the ground. Perfect. So welcome to the neighborhood, Mr. Rogers. In Pittsburgh speak. We're going to come right in on here. And Zion, come on in. And Troy, we're going to let you host the tour. And if you don't mind, you can point to Zion and say, hey, take a focus look in on this. I mean, obviously, you want to see us in nice uniform, by the way. You want to see us, but these guys really want to see this stuff over here, okay?
Right. So this is a live look at the components that we showed in the video today. Each one of the reactor electrode combination runs off its own specific channel that we can control and modulate remotely, make any adjustments we need to. This is our EBR controller. If you can kind of focus in here on the display, you can see right now we're running our reactor on channel 4. And you can see we're getting a reading on our amperage and voltage from channel 4. You see the other ones are showing 0. They're powered down. We don't have reactors and electrodes running there. And we can go to another view of this and see more detail on that specific device. We're on channel 4. We want to monitor. We're going to look at our reactor, and it'll bring up graphically what we're seeing on both amperage and voltage going to that reactor. So we get real-time response of how the system's running. If this cycle is long enough, we may be able to see the voltage go through a polarity shift. Each one of these is timed with a specific polarity shift between the reactors. Actually, you can see that now. You see our voltage dropping down. The amperage bottoms out during that polarity shift, and then you see the amperage come back up and the voltage then reading negative as it goes through. These are on specific time and for each specific controller as it's running when we modulate and change that polarity. This component, this is our cellular connection, where, again, if we have, and obviously here in Pittsburgh, so close to downtown, we've got great cell signal here. We can vary the carrier based on who has the best signal available in that specific location, and bring it, because obviously all of our communications go through that cellular connection. And we've done that in previous applications. We had to shift from one carrier to the other based on location and who was optimized to do that. So we do have that capability. Right now we do have one of the reactors, as we see here. This is on channel 4. This is actually the wiring for that reactor. If we were running the electrodes also, they would be connected here for the electrode in channel 4. Obviously, this specific panel runs channels 4, 5, and 6. The panel here to my left runs channels 1, 2, and 3. And our panel here runs channels 7, 8, 9, and 10. So we could run up to, with this specific system, we could run up to 10 total reactors. The system runs on 110 single phase. We have power coming in. actually goes to our step-up transformer. And actually kicks it up to 250 single phase, which is what the Israeli power grid works off of. And then we have movement from AC, kick it down to DC, and then we can modulate that current and voltage. Right now we're running 8.2 volts up to a max. I think we can run max of 13.4. But based on the performance of the system, that's where we can make these adjustments to our amperages and voltages. We can also track our electrodes as the electrodes are running to see what that gradient is that we're generating there. And again, the whole we want to pass a specific current density through that electrode. What the goal here is to accelerate that oxidation and release of the iron particles. So everything here, and again, if you remember that one picture, I was actually sitting right here working with the controller, had my voltmeter out, and I was on the phone actually with my colleagues in Israel who are looking at the same thing I'm looking at. They can log in real time from Israel to the controller, see the same things I'm seeing, and make whatever modifications or adjustments are required. Everything is contained, self-contained within the trailer. All of our cabling comes in from underneath. As you can see, this is a very clean setup, the way everything is laid out and designed. Any of the components that may need any maintenance to them, everything's modular. We actually had one of our subcontrollers for channel 2. We had a technical glitch with that subcontroller. I was able to disconnect these components, pull off that subcontroller for channel 2, send that back to my colleagues over in Israel. They were able to troubleshoot it, make the corrections they needed, send it back to me, and we were able to get that channel back online. Typically what I like to do, we run a max of 6 of the channels at one time, so we've run 6 reactor electrode pairs. But when I'm looking at sites, if we're doing a pilot, if we were going to spec out a system, I always want one spare channel in case we have a glitch or an issue with one of the channels we're operating. I have one on standby that we can move to and go. We'll jump outside if you want to step down. If you remember the one photo, you could see the reactor in that tank of water when Mitch and I and our teams were out in Israel, and I said we're effervescing, we're actually generating that reactive oxygen, converting that water to oxygen, and that's what we set up here. We were able to take this is just a display pipe, fill it with water, and this is that electrode, the reactor that we have running off of channel 4. And again, we were able to monitor that amperage and voltage that we were sending to this unit. And if you see here, I don't know if you can come in, you can see that effervescence. That's that reactor on that catalytic surface. We're able to convert that water. In this case, it's water, not groundwater, but that's the first step in that process where we are converting that water over to elemental oxygen. The one thing I didn't cover in my presentation that I will here real quickly is what's the maintenance to my system? What do I have to do? From an operational standpoint, we can make whatever modifications we can remotely anywhere we have a connection. But bear in mind, we have components in a well with groundwater and whatever sediment may be present there. Typical maintenance that's required would be on about a 4 to 6 week interval, and again, it's going to depend on the system and the quality of that specific groundwater. We need to shut the system down, pull our reactors and inspect them and clean them. This is a cleaning setup that I actually made in my basement. 4-inch PVC pipe on Christmas tree stands. So to descale and clean each of the reactors, we actually do a 15% hydrochloric acid solution. So I take a gallon of muriatic acid, which is 32% hydrochloric, and a gallon of water, and I make a cleaning solution. And once I've extracted the reactor from the well, I bring it over to the cleaning station, and we literally just drop it in, and 4 or 5 times, we just kind of dunk it up and down, let the cleaning happen, and if there is, a lot of times we'll get like, almost like a calcification scale, which again, it's going to depend on the groundwater condition, but it rapidly dissipates. We've got it cleaned off. I'll bring it up. I'll let it drain. We'll drain it back in, and then I'll take it over to this vessel, which is just full of DI water. We'll do the same sort of rinsing. We'll rinse it off, and then it's ready for redeployment back into the well. The other thing that we do at that time when we're cleaning our reactors is to inspect our electrodes. This is the one consumable part of the system. You know, we are forcing these metal rods to corrode. So at some point in time, they're going to be completely corroded and they need replaced. Generally speaking, depending on the current densities we're using, that's about 10 to 12 months. So what we'll do when we first deploy the system, before we deploy the electrodes down into the well, we'll take a weight. I'll actually do a weight measure on this to see what this weighs. And then in those 4 to 6 week intervals, when we pull it out, I'll weigh it again. So I can get a mass loss over that 4 to 6 week time period. We lost this amount of mass. Again, this allows us to do predictive maintenance that, okay, I know what this thing weighed when it started. When it gets to 15% of that mass, I'm going to replace it with a new one. And we can track that. And after usually about 3 or 4 of those iterations, we'll get a good handle on when this specific unit's going to need to be replaced. So the typical deployment arrangement for this, the electrode's going to sit about 1/2 meter or 1.5 feet below the reactor. And again, so if you imagine this being our 4-inch well, and we're generating our oxygen, and again, converting it to hydrogen peroxide on the cathodic surface. Down below that, we're going to have our reactor that we're forcing that current density through, releasing the iron particles. The one thing you'll see on the electrode, we've got a thin 1/4-inch tube. The trailer is actually equipped with a small air unit. We're passing a low flow amount of air down through this, and the reason we're creating an air lift, we're going to bubble a small amount of air through that, and the reason behind that is to suspend those iron particles and pull them up into this zone so that as those iron particles release from here, they don't just drop to the bottom of the well. So we're going to run some oxygen through here. We can monitor that flow. I know Doug and I have talked about putting gauges on there that we could monitor, because we're flowing from one specific air compressor out to all of our different units that we can throttle it back or increase that oxygen as needed. And again, those are kind of lessons learned out in the field. So those are our primary components that we have. Now, like with the gear that Mitchell has, we have a couple different options, and we've done it multiple ways. What we have, this is an
AP2000.
An AP2000. So we've got the SON deployed directly in what would be our EBR well. We've also done this in nearby monitoring wells. We've spaced them 5 feet, 10 feet, 20 feet, and that allows us, through their platform, to capture this information real time and see what our primary thing that we're tracking for influence from the EBR system is that groundwater ORP. Typically, we're starting somewhat reducing, again, we're generating ORPs, 600 and greater. How long does that effect take to get to 5 feet? How long does it take to get to 10 feet? How long does it take to get to 20 feet? And we can, through their capabilities of pulling this data, charting it, maintaining it on the cloud, we can track that time and see what that influence is radially and determine what that ROI is. So you've got a unit up and running right now, correct?
That's right. And so perfect segue, because what we're going to do is turn this back over to John Wright back out in Nevada. We've taken the AP2000 that you saw up there, and we've now submerged it inside the well. We're going to collect some real-time data, and if all this works out, we're going to reappear in the other room for Doug's presentation, and John is going to fill up the space by actually showing you the data that's being collected in real time. Now, again, we didn't put that in because we wanted to make sure that you could see the bubbling effect that the reactor is generating, but now we've dummied it in and put it in there. And it's more about just the demonstration of the fact that in real time we can project that data out through the internet.
Right.
So with that, and hopefully those guys, yep.
One thing I'd like to mention, you can see here, this is our power that we ran today to power up the controller. And what Doug's going to discuss in our most recent project that Doug was in charge of, when we pulled power for the trailer at his site, we had a meter right off the drop. So they were able to take readings. They took them every Friday. So we knew on a week's consumption how much energy the entire system was drawing. So that's the energy required to power each of the control panels, as well as what we were supplying to each of the reactor electrodes. And that's a part of Doug's presentation coming up here shortly.
Yeah, excellent point. So that would have been in the field. There'd been an actual electric meter out there.
And that was one of the, to me, one of many great things with this most recent project. We had estimations before that. We were estimating how much energy consumption we would have. Now we had true, actual, at 10 o'clock every Friday morning, Doug's guys in the field were out pulling that number. I think they were taking pictures for us. So we got that data on, spot on. Now we know exactly what it was to run the 3 panels, run 4 reactor electrode sets. We know what our energy consumption was for the system.
So when Doug's presentation shows up, we have a high degree of reliability in the consumption number now that previously we had calculated but weren't really positive about.
Right,
yeah?
Exactly.
Perfect, excellent. So we're going to switch it back to John Wright. John, I hope you're in there. You could take it away, and hopefully behind the scenes, those guys who are doing the production part of this are going to switch us back over there. And so, John Wright, the ball is now in your court again.
Thanks. Hey, thanks, Mitchell. Thanks, Mitchell. Thanks, Troy. Yeah, so what I brought up on the screen in the presentation there, monitoring point 1, the top device. You can see there on our web interface, we have a lot of intuitive tools. You can see here our cellular modem that Mitchell was showing you are the first icons on the left, showing you the power and the signal strength from the modem. The green behind the scenes there indicates that the device is current. If you look over here, I actually have this. This is actually in Israel time zone, kind of on purpose while we were teeing up some demonstration stuff last night. So the timestamp of 21:20 is Israeli time. But you'll notice there the real-time readings of the SON depth that is deployed in that tube. The parameters that are coming in, as I mentioned during the performance monitoring aspect of those values, ORP specifically, important conductivity temp indicators, and the high DO from that tube. If I click on the device itself, you'll see the data behind the scenes. So this is your data collector. We have this coming in at 5-second intervals. So it's pretty aggressive. I did that more for the live feel of it. Typically, we would do 30 seconds, maybe 1 minute data points. That gives us a lot of granularity to mostly a static data set. Again, we're looking for those breakthroughs to happen, that kind of behavior. So a good granular data set is nice. It kind of keeps us connected, keeps us with diagnostic tools, and then we can digest this all down to export where you can do things like 15-minute or 1 hour averages of your data to really make it digestible and reportable and graphable on your end. If I go to the chart, you can see we actually had this operational in the shop all morning, where you can see it's fairly flatlined while it was sitting in some clean water in a tube. And then it's a little bit hard to see at the scale, but you can see where it was recently deployed then in the actual EBR tube with some bubbling and reaction happening. We're getting that variation in the data. If I go back to the interface view, I mentioned during the presentation, this classic site summary view is giving you your operational data from the six, in this case, 6 EBR wells that are all connected to that controller. The ones that are showing red at the bottom, that's an on-purpose condition. The trailer, for instance, is set up for additional wells that are just not activated. So the device gumballs, we call them, are red, showing ones that are not active. We did have what we call two monitoring points back in our shop. We were actually testing the water quality sondes on 2 different modems and going back and forth between those 2 points. So that, again, just to show you some variety and variation between the diagnostic tools that we have available on our interface. And I'm going to do a quick reload of the application because I think I overwhelmed my browser with clicking around. There you go. So again, our GIS view is a full GIS location of, 1 second here, of showing the positions of wells, of showing the position of controllers. We can do, just to mention before I transition back to Mitch, I think they're ready, that our platform also can handle a lot of other widgets, gadgets, and sensors, perhaps meteorological stations, rain gauges, particulate monitors, sound and noise meters, multi-gas, single gas detection. All of those can be hung on the same platform. So in conjunction with perhaps an EBR project and some other parameters that you're measuring around that site, we can hook these all on. Mitchell, I see you waving at me. Back to you.
John, that's good. Hey, pan out so everyone can see where that site is, if you don't mind.
Let me get right back to it.
It's pretty dramatic when you're looking at it.
Yeah, it's going to pan slowly if you can hear me.
Maybe not.
We're gonna get a little echo. Go ahead, ask him for yourself.
There he goes. I don't think his connection, his internet connection where he's at is probably all that strong. Because on my computer, that rolls right out as a screen bar. You can just roll it right away. Anyways, while we're waiting for that to paint. So, again, the concept for today's whole presentation was developed at Battelle back in June, where this was kind of going on individually, and we couldn't walk through the whole thing. And it was really while we were attending Doug's talk that it sort of came to light that we thought, wow, we should actually get together and show everybody this all at one time. So the components of what we're talking about actually make sense. And so that was the idea. Doug was gracious enough to join us. His client was also gracious enough to allow us to be able to speak about that with their data. Look, John's finally got us where it shows him showing the Mediterranean. Not a bad place to be if you can get there. Anyways, with that, Doug, I want to say thanks for joining us to everybody. You can see, and the show is yours, buddy.
All right. Thank you. Thank you, Mitch. Thanks, everybody. Good morning, good afternoon, good evening to everyone, wherever you might be. It is a pleasure to talk to you today. Do I need, am I going through?
Yeah, you're good.
Okay. So we're going to talk today about our field scale pilot study, where we employed not only the EBR reactors, but the field data solutions, as well as a number of other technologies as we went through this. So when I started thinking about this, and I was getting ready to present at Battelle, and as Mitch mentioned, this is a larger venue, obviously with respect to time. I had 18 minutes. So I said to myself, geez, you know, what do you do when you got 186 days of pilot study and 2 separate areas and nearly 10 million data points? And my dog kind of freaked out when we did that. And then if you're not a dog lover, you know, even cats will freak out on this. So just a little bit of levity to start things off. We're going to go through and really talk about today. I'll give you a little bit of background on the site history. We'll talk about the layouts that we had for the EBR reactors. And then we'll talk about the results, and we'll end up with some takeaways, lessons learned, and then we'll have some time for questions and answers, hopefully. So what you're seeing here is a 1 mile long, this was a pipeline release. The release occurred right about here. We got kind of lucky in the sense of it was one constituent, benzene. Almost somewhere estimated between 10 and 20,000 gallons of benzene leaked out of the pipeline and has pretty much impacted all along here. This was back many decades ago. Just to give you an idea what the area looks like, and this also played into the whole evaluation and implementation. This was the line that I'm pointing to right here that leaked. On either side of it are high pressure gas lines and a number of other abandoned lines. So infrastructure wise, there's a ton of stuff in the ground still here. We had to work around it. It further complicates, obviously, you know, remediating a site like this. Oops, I went too far. Little bit of a timeline. So as I mentioned, that release was back in the late 70s. There was a number of years of investigation, characterization, ultimately ending up in the installation. The very first thing was obviously the spill response. Then that led to a groundwater interceptor trench that was 1 mile long and operated for a number of years until kind of had diminishing returns with respect to mass being collected. So they did some initial feasibility work and kind of settled on, we looked at ISCO initially, but the problems that Troy pointed out with respect to high concentrations and not being able to deliver, you know, a lot of reactive oxygen species in any one event, it worked, but it quickly rebounded and would have required, you know, literally probably hundreds of events. So they settled on it trying to do a multi-phase extraction, and they looked at it both in the native environment, which is, and I'll show you some pictures of that here in a second. That was a weathered clay, fractured, and then they hydraulically fractured that same clay to see if they could improve the MPE system. Settled on doing that, had intended, when they went full scale with the MPE system, to treat that mile-long area in 6 stages, about 800 feet per stage. Implemented the first stage, did the enhanced fracturing, and operated that system for around 5 years till they started to get diminishing returns in 2018 when they kind of shut the system down to take stock of what was going on. Enter 2019 when Jim Mueller and I had a conversation at one of the Battelle conferences about this new EBR technology. And I said, that's pretty cool. We need to find someplace where we can use this. Of course, 2020, COVID, 2021, COVID, took 3 years till 2023 till we could actually get this into the field. But that's when we settled on, okay, we're actually going to do the pilot study here. So in all of that time, they had done some initial investigative work and kind of delineated. And so there's our problem. You can see it's well contained laterally, doesn't go very deep, ranges from 9 to say 15 feet below ground surface. Here's where the current stage 1 of the MPE system is. This area highlighted in blue is where we did our pilot study. And we had a reason for doing that, which I'll get to in a second. So here is a core sample from the native clays. And you can see the fracturing and the oxidation within the fracturing. And you can even see it from a vertical perspective here. So this is the kind of material that we were dealing with. You can see why, A, it's hard to do ISCO in this, why, B, they needed to do hydraulic fracturing to try and improve the MPE system. Here's the initial collection trench that they put in. As I mentioned, a mile long, sump in the center. Our test area was right in about this area of the trench. That trench is still there. There's still impacted water in it. It's no longer operational. And we'll talk about some unique things that we've thought about with respect to the EBR on potentially treating this water outside of treating the spill area. This was their MPE pilot study, and you'll notice the MPE wells, CADOX unit, and all the equipment that was needed to do this testing. And there's some information over here on the side. They did these pilots in both areas, in that unfractured area. Then they moved down to the right of that picture and hydraulically fractured the clays, and then repeated the same test again. In both of those tests, they ended up recovering about 1,600 pounds of benzene over a kind of a 9-month pilot study. The next shot you'll see, so there is a picture of the clay and the hydraulic fracturing, just to show you that, you know, there is a difference in these two areas. And we took advantage of that. And that's, we'll end up here with, that is the picture of the full-scale system. You can see it's a beast, right? Huge, tremendous power requirements. You know, just to turn the lights on and run the blowers and the catalytic oxidizers was somewhere between $7,000 and $10,000 a month in just electrical costs. That didn't include going out to the site, labor, everything else that was associated with it. So obviously finding a better mousetrap was really important. So 2019, as I mentioned, was a landmark year. After they'd shut the system down, we stepped back and said, we got to look at a different strategy here. What do we really need to deal with a cleanup the size of this and as remote of a location as it is? Well, we needed something that was passive and self-sustaining. We didn't want to have to transport any materials off-site, and we wanted to be able to have a continuing reduction in the contaminant mass and the least cost of ownership related to that. With respect to our overall objectives, we're trying to get numbers in the soils down below 400 milligrams per kilogram. That's less than CSAT numbers. Long term, even lower. Groundwater, nobody uses the groundwater there. This is a, you know, you can pump every well there dry in about 30 seconds. So it was just to reduce that potential, keeping it from getting into other potential receptors, whether it was discharge into surface water or whatever, and then, you know, ultimately end up where we met our soil remediation numbers and we can just go to some kind of natural attenuation phase. But we need to get from where we are to where we wanted to be. Step in, EBR system layout. So as I mentioned, you know, let me go back to the objectives here real quick. Sorry about that. Got a little. We wanted to evaluate the EBR system to see how it addressed the, the efficient removal of benzene from both soil and groundwater. That was important. Evaluate the kind of, operational performance. Does it work better in fractured or unfractured or the native fracturing? And then determine what kind of operational parameters and data requirements, if we take this to full scale, what are the things we kind of need to focus on? And then an economic comparison, primarily looking at electrical costs to start with. So as I mentioned, we utilized that previous test area, already had pretty much everything that we needed set up in it already. Piezometers had been drilled at radial distances away from these 4-inch wells. Those 4-inch wells are what we use to deploy the EBR reactors. In the unfractured area, they had tested kind of a gridded pattern, about 30 foot on center with those wells. In the fractured area, they went with a linear approach, still about 30 foot on centers, but you can see that the orientations were a little bit different as well. Up on the top, I won't strain your eyes on that. We'll look at individually. When we went into the unfractured area, so here we're zooming in, you can see the 4-inch wells that we use for the EBR reactors. These were 1-inch piezometers. We drilled 5 new 2-inch monitoring wells to collect additional data, some of which we deployed sondes in, others we had in the EBR reactors as well too. That was our unfractured area. In the fractured area, concept was the same. We just arranged things a little bit different. Again, the 1-inch piezometers, the EBR reactors, and 5 monitoring wells in this location, 2 in between the reactors, and 2 that were perpendicular to the line of reactors. Just some pictures from the site. You've seen some of these. Here's a picture of the reactor and the electrodes laid out on the ground. This is an installed reactor with all the cabling tucked away, nicely tucked up. And here's what both sides looked like just before we started the tests in either of the 2 areas. So you can see the gray boxes that John talked about with respect to all of the communications equipment for the downhole sondes, our reactors, all the cabling and everything that went into the trailer. And you'll notice that power pole right behind the trailer. We also had a power meter on that power pole so that we could evaluate electrical usage throughout the test. Next, a real quick picture, just zoomed in on the reactor and the electrodes. As Troy mentioned, that's how they get deployed in the well. For his live demo, he mentioned about 18 inches in between those, and that's how it all gets dropped down into the well. Few last photos again showing the sondes, the cleaning and O&M that Troy talked about. Again, you can see this is after we had operated the system for a while. There's the corrosion of the electrodes. Here's the air pump that Troy mentioned that sits in the corner of the trailer, and you can see the lines going to our 4 reactors, and again, the EBR reactor here. So with that all queued up, let's talk about results. We'll look at those in both, first the unfractured area, then we'll look at the fractured area, and we'll get through this discussion, and then we'll move into lessons learned and our takeaways. So prior to starting off the test, we took baseline numbers, and we're going to focus primarily on pH, DO, and ORP, and that's how you'll see these presented in all the subsequent slides. But you can see that, in general, these wells were pretty well, pH is pretty neutral, with the exception of the monitoring wells that had just been installed, still had some elevated pH because of the newness of the wells. DO was, there and present, anywhere from 1 to, maybe 2 ppm. And we kind of had this variable ORP to start with in all these wells. Some were pretty close to, 0 millivolts. Others, the new monitoring wells, were slightly higher. And some of those piezometers, they were, anywhere from, to as much as almost minus 100 millivolts. So kind of a slightly reducing environment. Had all this data for baseline, turned on the system. And what we'll see here is a summary of all of the data from the 94 days that we operated in the unfractured area. Again, pH on the top row, DO in the middle, ORP in the bottom. So what do we see here? First thing we see is pH stays relatively neutral through the entire thing. So we didn't cause any kind of significant pH change that would tend to mobilize metals if you had them, for instance. But immediately we see within 10 days, all of the EBR reactors, and then we took data and averaged it over a week events. So within that first week, we had gone from roughly 2 to almost between 12 and 14 milligrams per liter of DO. What we see in our monitoring wells in between the reactors is a kind of continuous increase in that as that radius of influence expands. And again, you can see that same thing in these piezometers. The real key data was looking at the ORP numbers. Immediately, when we get the reactors on, we see ORPs that are up, near plus 800. And then we see in these 5, 10, 15 foot away reactors, we see this progressive. UP4 was closest, UP5 was the next closest, and UP6 was the farthest away. We see that response. So we knew, looking at this data, that we were getting out at least to that 15-foot radius of influence. Concentration data. We took initial both soil and groundwater concentration data. These are groundwater data here. You can see it was pretty smoking here. 600 parts per million, roughly, in the groundwater. Every one of these are separate events. We did not sample every well at every event. Obviously, we don't have over tons of funding, but we did take so that we at least had multiple samples from every well on the site at least 2 or 3 times throughout the process. What you immediately notice is, and then the purple bars are about 60 days after we shut down the system. And you'll see that they rebound some, but still nowhere near what our starting concentrations were. In the EBR reactors themselves, exceptional reductions. I mean, we went from hundreds of parts per million down into the low part per billion numbers in a mere 90 days while these things were operating. We did, as I said, we did see some minor rebound, but that makes sense. We made a clean island in the middle of a kind of dirty sea, and once we shut things down, everything kind of started trying to go back to where it was before. Had we let this run longer, these numbers would have been even better. From a percentage perspective, if you look at the percentage changes, the EBR reactors had roughly 3 orders of magnitude greater than 99% reductions in the groundwater concentrations. The piezometers were in that 80 to 90% range, and the monitoring wells, particularly the ones in between reactors, almost anywhere from almost 2 orders of magnitude to nearly 90%. And the wells that were kind of outside still had some influence, but not as much as the wells that were in between. So this gave us an idea on, okay, this is what a gridded approach would look like. Had we had this to do again and you were actually installing it, you wouldn't actually put them on square grids. You would be more likely to offset them so that you got those overlapping cones of influence. That's groundwater concentrations. Then we took a look at soil concentrations. We went and drilled immediately next to these wells, same general locations as we had taken our soil samples. And what we saw was in the EBR reactors and the two monitoring wells that were in between multiple reactors, roughly 20 to 30% decrease in the soil concentrations. And these soil concentrations, again, were in the parts per million, milligrams per kilogram, hundreds of milligrams per kilogram. Some of the wells didn't change all that much, probably analytical variation. So we knew that we were getting some mass off of the system. We knew we were getting into the dissolve phase where the reactive oxygen species can work on it way more efficiently. Troy mentioned follow-on bio. So we were curious about that as well. So we did do some qPCR work. Black bars are pre-pilot, yellow bars are post-pilot, and these are data broke out for an EBR reactor. And we said, well, gee, if there's going to be real harm to the microbial populations, it's going to be where the reactor is the hottest at. Surprisingly, not a huge difference pre and post. So we know that with the additional oxygen that's there, the fact that we still have these microbes, we can promote enhanced biological degradation. In a well in between this, we looked at the similar results, and we still see, really good numbers for our aerobic degraders, which means that there's a good chance that we've stimulated follow-on bio. We have not been funded for sampling to go out and look at this in more detail, but this is just what we could glean over our study period. So then we switched our focus to the soils, and we said, well, how can we try and get a handle on how this material might be coming off of the soils? Are we driving material off the soils? Well, the KD value is basically, simply the concentration in the soils over the concentration in the water. So if we look at our baseline numbers, and then we look at numbers that were treated at post-treatment, and we did it in two different events. One immediately after shutdown, which is the top numbers here, and then about 30 days, excuse me, after we shut the system down. And what we see here is that obviously, since these numbers go up, that's a direct result of the low groundwater concentrations. But when we get out a little farther, those groundwater concentrations, what did I do? Time out for a second. Oh, we're back? Okay. Okay. So what we saw here then is that even in some cases then, we did have numbers, KD numbers, that were lower, meaning that this numerator had to go down some too. That gave us kind of the warm and fuzzy that, yeah, we were desorbing some mass from the soil and getting it out into the dissolve phase. This is in the fractured zone. We'll show the same data for the fractured zone. This is the unfractured zone, and you'll see there was a difference. Power, we talked about usage. We did monitor our power usage every week on Fridays, as was mentioned, and using two different kind of rates, either a summer rate or their normally published rate. We looked at the cost per day. And when you do the math, this system with 4 SONs, 4 reactors, the control trailer, all of the equipment that we were using to put this thing together, run computers in the trailers, it ran somewhere between $6 and $11 a day, depending on what rate you use. But you can see once we started it up, it was very consistent. through the entire time frame. We'll again look at this in the fractured area as well in the next set of slides here. So let's move to the fractured area. Going to see the same format of the presentation here. Again, pH, DO, ORP. Here you can see we were a little bit more oxidizing in the fractured area. Kind of makes sense. There's a little bit better communication. Water gets down a little bit easier because they've hydraulically fractured this area. But again, pH, relatively circumneutral. Again, DO's reasonably, around 2. And ORPs, were a little bit more oxidizing than in the unfractured area. But yet you'll still see that there was a big difference once we turned the reactors on. So what did that test look like? Again, about 94 days that we ran that. pH again remained relatively consistent throughout the whole thing. DOs, as you can see in our EBR wells here, immediately shot up in that 12 to 14 or higher milligrams per liter. Again, you can see in our monitoring wells, and in particular, the 2 wells that are on the top of this graph are the wells that are in between the reactors, and the other wells that are perpendicular, you see they were kind of muted, but that's because they were oriented perpendicular to that linear deployment with the EBRs. And again, in our piezometers, we can see gradual increase in DO throughout the entire test period. ORPs, again, 7 to 800. Here again, you can see around 40 days, we started seeing results in those 2 reactors, or the 2 monitoring wells in between our reactors. Perpendicular to it, not as much. In our piezometers, again, continuous increase in our ORP numbers as we went through this. Hold on 1 second, my mic just came. Okay, now we're moving to the groundwater concentrations. In this particular area, and as you saw from that original investigation map, concentrations varied across this spill release area. Shouldn't be a surprise to anybody. They were about 300 parts per million lower in this area, but still pretty high. I mean, in the 300 part per million range. And these are those 6 piezometers. And you can see we had, easily by the end, 2, maybe 3 orders of magnitude decrease in some cases. And notably, in those wells, where this was a fairly highly fractured area, we didn't see the rebound in our post-pilot monitoring. So that told us maybe fracturing does help. But there's a trade-off. It costs money to put fractures in. So the question is, how long do you need to run this system in either state before you can really get enough data to evaluate that economically? We haven't gotten to that point yet. But again, extremely good reductions, multiple orders of magnitude in our EBR wells, and even in the monitoring wells. What was unique here was we saw decreases, but we didn't see as much as what we thought we would, even though we knew the wells were in communication with each other. And our theory is that because we were more effectively desorbing the soil mass into the dissolve phase, we just were replenishing it as we were destroying it. Otherwise, we wouldn't have seen these lower soil concentrations. So if we take that and convert it to percentages, again, you can see 2, 3 orders of magnitude decreases in all the EBR reactors. In all of the piezometers, at least 90% or greater. But we saw increases in some of the monitoring wells. These not so much, probably because they weren't in the radius of influence, but these probably a direct reflection of desorbing that mass from the soils, getting it out into the groundwater. From a percentage perspective, when we look at our soil concentrations, much better in this fractured area, right? In those two wells that are in between the reactors, you know, up to 40% decreases. Even here, much more significant percent decreases in the soil concentrations when we looked at this data overall. Does that mean fracturing is better? Maybe. But again, it's going to come down to a cost. How much it costs to fracture versus what advantage you gain with respect to operational time. Microbial populations. Again, black pre, yellow post. Here we did see, you know, some slight increases in some of our aerobic degraders post follow-on, probably due to the fact that, again, there's a little bit better communication with the water in these fractured areas versus the unfractured, or this native fracturing. And again, even in between the wells, we see, you know, reasonable and particularly the abundance of a lot of aerobic degraders. So now let's look at the KD, the differences I talked about in the KD values. Here, same type of calculations, but what we see, untreated versus treated immediately post, we now see, you know, much lower numbers, indicating not only is this number lower, but this number is lower as well. And more so than that got lowered, or we would have still seen a equivalent ratio. So that really, you know, told us that we were transferring mass from the soils into the groundwater. Power usage in this area. Now that we kind of had things up and running, we weren't running some of the equipment we had. We had a small tick downwards in our actual power usage, and it actually was somewhere between $4 and $8 a day in this area for the same amount of time, 90 some days of operation. So if you do the math and average everything, about 10 bucks a day to run 4 of these wells plus all the associated equipment that went along with this, compared to $10,000 a month to run the MPE system. So with that, almost to the point of wrapping up here, what were our takeaways? What did we learn? And then we can move in to open the whole thing up for Q&A. So let's take a look at our unfractured area first. First and foremost, super robust operations. This thing ran nearly 100% of the time. We were down for 5 hours due to an electrical storm one night. As soon as the power came back on, the system booted itself back up, started running just like it had never been turned off before. Never even had to go out to the site. It just came back alive. The real-time monitoring, super effective. You know, we collected data, an overabundance of data. As I mentioned, it was nearly 10 million data points. We were collecting data every 30 seconds, basically, from every one of those sondes. It was up 100% of the time as well, absent that 5-hour time when there was no cell tower, there was no power, etc. And the O&M, as Troy mentioned, simple. We went out every month, shut the system off, pulled the reactors, rinsed them, put them back in. The whole event took 3 hours maybe to do from start to finish, from getting on site till they left. So minimal O&M during this entire operation. From a results perspective, stable pH. We saw increases in the DOs. We saw that DO front propagate. ORP, we saw that. That allowed us to estimate this ROI somewhere around 15 feet by the end of this. So that would mean that if we were going bigger with this system, we could install wells approximately 30 feet apart, give or take. One reactor was sufficient to treat that entire 8-foot impacted zone, and that makes sense. The thing takes up about 7 feet, so we didn't see any need to have multiple reactors in the well that would to ultimately get to, where we would want to get to. Soil results, we saw moderate decreases, saw some rebounding, again, because we cleaned up a clean spot in the middle of a dirty sea. Nothing really remarkable with microbial changes, and our operational costs we talked about. So, we were really pleased with the results that we got. Let's take a look at the fractured area. Again, no power outages this time, ran 100% of the time from the time we turned it on till the time we went out and shut it off. Real-time monitoring performed well here. However, we started to experience in this area some electrical field interferences. And we think that has to do with the fact that there's 8 pipelines buried underneath there. We were generating fields. They have cathodic protection on those 2 high-pressure gas lines. It started to make the sondes go a little crazy. So we had some issues, and we tried a whole bunch of things. John got tired of talking to me from trying things, and Mitch was sending stuff out there, different units. We tried everything, and it just got confused in this event. So that was the only kind of weird thing that happened during the entire time. Again, O&M every month, just like we did before, never had an issue. We won't go back through in detail, but we saw, slightly faster indications of increases in DO and ORP as we went through this, indicating that, yeah, maybe the fractures do help it. But again, we still need to look at, well, what does that mean from a full-scale perspective, and operationally, is it worth doing it or not? Lessons learned, and this is getting to the end here. So this system is extremely robust. It really is. It was successful at both dissolved phase groundwater and soil, reducing those concentrations. Granted, we had a single constituent here, but again, no reason to believe if it was mixed constituents, and you saw some of the case studies that Troy presented, can handle chlorinateds. It can handle, typical, petroleum hydrocarbon releases. This just happened to be benzene. The monitoring, extremely valuable, really, really excellent to be able to go in and get that data, work with it, pull averages out, and then work with data that's based on a lot of information to give you trends. Power, significantly better than the current system that they're running, obviously. Even if we ramped up to 40 units, and you take a straight 10x and you say, okay, that's $100 a day to run 40 units, that's still $3,000 a month versus $10,000 a month. That's still a 70% savings in your power. Fracturing, that one's still, it's out there to be thought about. From the perspective of, are there advantages to doing it? Would we recognize shorter cleanup times by fracturing? Fractures cost roughly $3,000 to $5,000 a fracture. So if you have to put a lot of fractures in, it's going to have to be a big difference to make it really cost effective. We are now currently looking at initial designs for full-scale systems to expand that. We'll start up in that phase 1 area where they already ran the MPE system, get additional data from that, and then start moving on the rest of it. And one of the other key things that we took away from this, I mentioned all the water in the groundwater collection trench. There's roughly, we estimated, almost 1 million gallons of water in that trench right now, potentially at 200 parts per million of benzene. We said, well, gee, we've got this whole infrastructure there. Could we use these EBR reactors in a slightly different manner, not in ground, but could we deploy them in some kind of vessel, pump the water, use the trench The sump is there, pump the water, treat that water, put it back into the trench, and basically treat that 1,000,000 gallons of benzene mass that's there to help bolster the rest of the system. So we ran some tests with the folks over in Israel, and lo and behold, it was pretty fast. What was it, like 2 days? They took some water from a gas station over there, which was almost equivalently impacted, and impacted with more than just benzene. And in fact, we think we can do it. So we've been kicking around with the client, possibly doing a small test, maybe, you know, starting off small in maybe 250-gallon container or something, and deploy a reactor and proof of concept. And then it would be as simple as bring in some frac tanks, pump water, fill up a frac tank, deploy 4 or 5 reactors in there, let it cook for a couple of days, pump that water back into the ends of the trenches, replace the water, and just keep going. So that's one of the things that we're looking at. Another use of potentially of the EBR system. So with that, I believe we can open up for questions. If, one more slide here that will help everybody on the line. If you want all my contact information, if you scan the QR code, it'll pop up and you'll have my phone number, email address, all of those things as well. So with that, I will wrap it up and we can get ready for some questions. Thanks for everybody's attention.
Doug, that was awesome. Thank you. Troy, excellent job. Thank you very much. John Wright, excellent job. Thank you very much. Appreciate you guys. I've been monitoring the chat, and so, the Q&A, excuse me, and I've got the questions lined up for you. I'm going to try to start in order of the presentations, and so that'll give some time in case something else comes in as well. So the first question was, can you describe the effect of soil type on ROI, sandy aquifer versus silty/clay?
That's a great question. One of the things that we wanted to prove in the test that we did with Doug at his site, not surprisingly, the technology being developed and first implemented over in Israel,
Sand.
it's sand with interstrewn, silicon clay lenses. We could go coastal here in the States and find that, but the United States is so much larger, we have greater lithology. And that's one of the things that conceptually, based on how the system operates, and being able to generate those reactive fronts, and the fact that we've got thermodynamic drivers that propagate those fronts outward. The concept was, as we went through it intellectually, we're going to be as effective in those more difficult lithologies. And we saw that.
I think the data speaks to it. I mean,
Yeah.
even in tight clays, now those clays had weathered fractures in them, granted, but they're not something you could drop a well in and provide even water to a house for. So it's really tight. And that's been the problem. That's why this problem has persisted for 40 years at this site, is because current technologies or previous technologies, while effective, are only limitedly effective. Here, we have the beauty of this is, it doesn't matter if it's tight. We're constantly supplying those reactive oxygen species. And when we do that, anytime a molecule runs into one of them, it reacts. The key is the reactive oxygen species is always there, and the molecule's not just out there by itself.
Right.
That's the beauty of this system.
And we saw similar, our previous deployment here in the States, I mentioned as I was going over where we've deployed it, we did a PRB deployment at an industrial landfill. That was actually a fractured rock type lithology. And we saw near mirror images. We actually got between 18 and 21 feet. Now, granted, that system ran longer in that specific period of time. And that's something that, Doug and I have talked about. Again, our pilot there was proof of concept. Will this affect positive change on those high contaminants. It wasn't, how long does this have to run to reach our remedial goals? That's yet to be determined, but we've tested in tight clays. I ran, similar 4-reactor. It was linear, similar to what we did in the fractured zone. In a fractured bedrock site that was deeper, we were at about 40 feet below surface instead of shallow here. And that's one thing I wanted to mention. Doug had talked about that, we had a single reactor electrode deployment to create to treat a specific vertical interval plane. If we had a thicker zone that we needed to treat, we have the capability to stack, so to speak, that reactor electrode combinations where we could put a set at 20 to 25 feet and then another set from 32 to 38. Again, the reactors and electrodes, they don't know what depth they're at. They're just going to do what the system does. So we have been effective in proving that this is more than capable of dealing with difficult soils.
And the other thing that was interesting to me is that this is a 3-dimensional radius of influence that
Right.
you really see here. It's not just
Right.
out in a circle around it in a cylinder. Even above and below where the reactors are deployed, you see changes.
Well, and that's one thing that I would say you failed to, but it wasn't included in your presentation. How's groundwater moving at that site?
It doesn't move,
It doesn't.
basically. It basically, such a low gradient, such low permeability, that it just is sitting there.
Right.
And hence why we've seen that long linear shapeform. It's moved along the pipeline corridor way easier than it moves out.
Right.
So it just, and I apologize, I did have that slide in another one, but I tried to get more data into this, and
Right.
I took that out in lieu of some of the other information. But yeah, no,
Right.
the groundwater is pretty stagnant at that site.
And that's the one with the test we did with Doug, and I know I do it, when we deploy traditional in situ chemical oxidants, we're looking at that flow of groundwater to help move and distribute our amendments in the subsurface. Here, this is really thermodynamically driven.
Yeah.
So we get it's not a teardrop from an injection point, it's truly radial with that EBR reactor sitting dead in the center.
Yep.
Okay, great. Next question, what does EBR stand for?
Electrobioremediation.
One more time.
Electrobioremediation.
We've been throwing that acronym around all day.
Right. And
sorry.
I know as practitioners, we're guilty of throwing out acronyms like everybody knows what we're talking about. So the concept behind that is we have that electro-driven remediation followed by onset bioremediation, post-treatment.
Next question. What is the redox mechanism that applies in EBRs for chlorinated volatile organic compounds dechlorination?
It would be the same as any oxidant type reaction that you're going to have, whether, pick your oxidant that you'd use to do chlorinateds. We're generating these reactive oxygen species, these highly, highly reactive that are going to be super, super effective on chlorinates. If you remember that chart I put up of the different oxidants and their oxidation potential, permanganate's effective at treating PC and TCE because that carbon-carbon bond energy of PC and TCE is less than 1.68 volts, which is the oxidation potential of permanganate. When you start generating these reactive oxygen species, which are almost double that oxidation potential, we can easily go after and treat chlorinated sites.
I'm a chemical engineer, not a chemist. But in
both.
talking with chemists, basically when you're talking with chlorinated organics, you get the substitution nucleophilic reaction, right? You've generated this radical oxidant species. It goes in, it pulls off chlorine, it replaces that.
It's attacking those pi level
and so
electrons.
right, exactly. And so it's a substitution reaction that's, you know, the SN2 that we learned about
Right.
grudgingly so many years ago.
Perfect. Next question. Can you use existing site wells and monitoring wells?
It's going to be based on size. You know, typically we want to deploy the reactor electrode pairs in 4-inch wells, just for ease of handling of the equipment. We actually attempted to deploy one of our electrodes in a 2-inch well, and it just won't fit. When we did that industrial landfill site, kind of the same thing. Can we use this? And it just won't work. So it depends on, yes, if your site has 4-inch wells screened at the interval you want to treat, we can go. We could actually do open borehole.
Yeah, and I was just going to say that at a site that Troy and I have been talking about, where we're planning on going and doing another and chlorinated site, we plan on drilling and it's deeper. We need to get down to about 60 feet where our really weathered bedrock zone is. And our plan is there to simply drill the 4-inch cased off at the surface and open borehole complete, you know, for the rest of it, and then deploy the reactors just as usual. But you don't need a well per se to do it. You just need access to the water.
To that zone you want to treat.
Exactly.
Yeah.
Gotcha.
And guys,
This
if I could
question, I
add,
think is for John. John, can you describe the nature of the connection from the unit and from the monitoring wells? And I'm presuming they mean to the cloud, et cetera.
sure. Can you guys, Doug, Troy, can you guys hear me locally there in Pittsburgh?
Either way.
Yes, we can hear you.
Okay, because just to add one thing to the thing about monitoring well diameters, the monitoring equipment, the sonde that I showed you, typically on our end, we're a 2-inch well for existing wells that are either on site or you need to install. Similar to Troy's answer on the operational side, if you have 1-inch piezometers or something like that, we could do single parameter sensors, like an ORP sensor, if that was appropriate for the way that the client wanted to implement on site. As far as the communication, Mitchell, great question. So the box that I showed you on each well, that was a 1-to-1 relationship of a cellular modem. So the sonde in the well came up to the top on the surface. A cellular modem was in that box and took that data up to our server directly. We do have the ability to do radio point-to-point communication. So on a larger site, where maybe it was more cost effective to have one cellular connection and maybe 12 wells, we could communicate all 12 wells back to a central point. And we do have the ability to communicate through Wi-Fi, satellite, some other technologies on difficult or on sites where cellular connections are not available.
Gotcha. Thanks, John.
Yep.
Another question for John. Are you monitoring an active site in Israel?
I saw that question come up on the chat. Maybe it was a little confusing when I showed the web interface. So we have access to the control aspect for that site in Israel that we've communicated with Provectus and El Gresse. So those are the operational data, the voltage and amperage from their wells. The water quality sonde is the one that you had in Pittsburgh that I meshed together onto one site for the demonstration. So we are not actively monitoring that project for water quality.
Gotcha. Thank you.
Yep.
That was my question, by the way.
No, yeah. Yeah, you probably wondered where the rental equipment went. No,
No
and
problem.
If we do, we're buying some multiple airline tickets. So.
Next question. This is a fairly lengthy question, and I believe this one is for Doug.
Uh-oh.
And so I'm going to actually read this directly from what they got here. Can you discuss the magnitude of contaminant rebound, i.e. TCE, during long-term post-remediation monitoring at sites with aquifers that include lenses of low permeability material that often cause rebound due to back diffusion? i.e., is there any documentation that the remediation method limits this behavior long term?
Well, I think Troy and I can tag team on that. First of all, well, this site was benzene, wasn't TCE, but the concept is still the same. Obviously, in an environment that you've described, we've got low permeability zones within a more permeable aquifer. It's well documented that those are sources of collection of mass, and then when you clean up the groundwater for a back diffusion or rebound as that material comes off. There's been tons of studies that have been done out in University of Colorado. Tom Sale's done them. A number of people have done them that clearly illustrate that it's not even a phenomenon. They clearly illustrate that it happens. The beauty of this system is that, assume for a minute that you've now cleaned up your groundwater to just non-detect, for instance. First thing you've done is you've set up a concentration gradient, which is going to promote that diffusion on a molecular basis, and from a purely mass flux perspective, you know, you now have a concentration gradient, just like groundwater moves from high to low. You now have a high concentration. It's going to want to release material into that. The rate at which it does that is dependent upon a number of things, obviously. But the beauty of the continuously supplying the oxidant to this is, and as you've seen from the sites in Israel to this site that had the high clay, you know, mostly clay, very little sand, if you're permeating all of those, you're reducing mass across everything, all at the same time. And if you do it long enough, I could envision you could preclude the mass rebounding, because you would actually have been able to, A, force it to desorb, and B, what doesn't desorb, you're still going to be able to get these reactive oxidant species into that pore space and destroy it from within. So you're almost doing 2 for 1. You're doing within and the diffusion part. I don't know that specifically answers your question. It doesn't give you a rate, but that's what I would envision seeing. And Troy, maybe you want to add to that.
Yeah, and that's the one thing, it's going to be the amount of time that the system operates. So obviously we can treat that groundwater most rapidly. And as Doug described, you set up that gradient then, which then drives that desorption. The other thing that we can do, if you've characterized your site and you know where those lower permeable locations are, we can target that more with where the actual location of the reactor is put. So we can focus on those low permeable zones.
Perfect. Okay. Follow-up question from the same person who was listening in today. Very impressive technology. However, it appears that total cost will be relatively high with all the monitoring, et cetera, required, except at very large site like Doug Gray's benzene case study. Please describe potential cost control options, if any, during full-scale operation.
What I'll go with that, the way I'll address that is how my colleagues in Israel address monitoring. They think we're nuts.
Yeah, they thought we were flat out crazy.
They thought what are you doing? When our colleagues in Israel go to a site, they deploy the system, turn it on. They can monitor it remotely like we discussed today and make any adjustments they can, but they're not on site. They leave it go for 4, 5, 6 months. They just let it work. And then they come back 4 to 6 months later, they actually have a tow behind trailer that runs flow through cells. They drop a line down, pull samples, run all of their quality parameters, gather their data, and haul that trailer on off. This is a new, innovative, unique technology here in the United States. Everybody wants to see data. Like Doug said, we collected over 10 million data points in 2 94-day operations. So if you want to see data, we
Yeah.
can give you data.
And I
So-
think, yeah, that's the point is we wanted to be able to kind of answer that exact question is what is important? You know, if you recall, one of the objectives was what is important to evaluate the efficacy of this. It may be as simple as ORP probes and not an entire sonde and not an entire array. Those are very low cost, very easy to monitor. You could do it remotely, or you could put them on and just like almost like a transducer.
Right.
And when you record data for 30 days, and when you go out to do the O&M, you pull those, you download your ORP data, and you come back and you look at it. It could be as simple as that. But the value of having the ability to look at that in real time, especially when you're first trying to understand how to tweak and optimize the system.
Exactly.
That was one of the real great advantages of this, is that we could see it. Oh yeah, we turned it on. Day 1, nothing really. Day 2, nothing really. And then gradually, and then by day 10, yeah, there's a noticeable difference here. We satisfied ourselves and our curiosity, and now have that information when we go to talk to a regulator or somebody else and they say, this looks like witchcraft to me. It's not. It's real.
I think John had something wanted to chime in on that answer.
Yeah, great question. How to present it where the monitoring, especially scaled up, could be significant. And as Troy mentioned, the opposite of that is the kind of known reaction with this in the lithology that exists on those sites in Israel, being very, in layman's terms, simple and understood. And in these pilot studies, we're trying to gather that base of information on what is important, what is not important, what's critical, what's helpful for a team to understand it. And as I showed you on those couple last slides, those various phases of monitoring where you're, pre-deployment background versus that really almost critical point that Doug's talking about, the turn the system on, and how many days or weeks does it take for the breakthrough to see that at that, especially a pilot study, you're having an effect at that desired radius of influence. So you can understand what's going on in your site. That's where I see this monitoring real time or semi-real time being important. And then as I mentioned in that slide, perhaps over 6 months, once that point hits, you scale back the real-time monitoring, maybe from 8 wells to 2 wells, real time. And then so there's a lot of variances in how that's implemented. And that's what we've learned during these first pilot studies and will continue to learn in the near future.
A lot of that is, what does your client need? If you recall the case studies that I presented from the sites in Israel, those are point data points. You can tell they went out at 5 months and pulled a point. They went out 3 weeks later and generated a point. Then you see what John put up, and you see these nice, smooth graphs, because that's real time. I mean, there's 30-second intervals between, instead of 3 weeks or 6 weeks, there's 30 seconds between each one of those points.
Right.
So a lot of it will get down to what's the need of your specific client.
Gotcha.
And it's kind of like the innovator, bell-shaped curve too, right? With this technology, we're got early adopters, and you're going to have people that you have to convince. So you need the data. You get out past to where this is mainstreamed, like it is in Israel, Nobody
Yeah.
cares about the data, they care about the results. So they've adopted it and they said, okay, we know it's gonna work, just tell us when it's done.
It might be a while before the US EPA
Yeah.
endorses it as a sealed and stamped technology.
Exactly.
Yeah, and we've.
Yeah, good
I-
point, Mitchell.
Jim Cummings and I have had those discussions at every conference, and one of my favorite people to talk to every time I see him.
Yep.
One last question, and then we'll get to the wrap. With an air sparge component with the EBR reactor, is there a need for SVE and air treatment?
It's
And
not.
I think it's the use of the air that you talked
Right,
about
right,
during
right.
there. Maybe you want to highlight.
Right, and I wouldn't term that an air sparge.
Did you see the pump?
I mean, think of a bubbler in a fish tank
Yeah.
is about what we're doing. And the whole idea is there's just enough air bubbles coming up through there to grab those, small particles of iron that are, being sloughed off from the electrode and suspend those up. We're not, you saw Doug's pictures of their SVE system and these huge air handlers. I'm running this through like a quarter inch tube. It's,
Yeah.
it's not, I wouldn't term it as an SVE or an air spark.
One of the things that Troy and I talked about while we were in the field was maybe we should measure this, because that might be a question. Oh, well, you got another mechanism going here. And we thought about doing it. We just didn't go there. But that is something that would be of interest. But the amount of airflow is so minute. It's mostly just a buoyancy thing. You're counteracting the buoyancy of the iron particles, that's all.
Excellent. Well, gentlemen, we actually do have a few more questions that we will get back to you on. I just want to address some issues because we're really bumping up against the time frame which we promised people. So let me just wrap by saying thank you to Doug Gray and your client as well for access to all of their data. We really appreciate that. Thanks to Troy for dragging the technology out here from Ohio, setting that up, and enduring the day you had yesterday with the traffic and the rain. Thanks to John Wright. Excellent job on the presentation. Someone had asked about slides, copies of slides. My suggestion would be, hey, reach out to these guys individually or through some electronic medium if you're looking for something specific. I'm sure they'd be happy to talk to you about that. I want to also thank all the folks behind the scenes here at FEI, Clarissa and Kelsey in particular, also Mike Waltman and Zion from our IT department for putting on the production, Chris Mullen out at Provectus, who I know was involved behind the scenes for doing that. Mike, if you don't mind putting that slide up that I had for you. So just so you know, if you have seen me speak before, this is a slide that I use often in my presentations, and I think Mike is going to successfully get it up there if he doesn't. I want to tell you that to all those people who were writing in and telling us, hey, we can hear John, there was probably 10 or 15 of you guys. I'm going to count that as a question, and we're going to add $1 to the kitty for the donation. So thank you for doing that, even though we couldn't hear them. And we don't work for Verizon. But this is, when I try to tell people about my experiences in the environmental industry, this slide sums it up, right? We always have the anticipated plan and the checkered flag at the end, right? In reality, this is how it happens. Behind the scenes, what you didn't see, us taking a couple of years off of Mike Waltman's life, was the fact that right before we were walking out the door with the camera, we realized it had 3 minutes of battery life. And so he quickly made a battery, not only a battery, but a camera change. and a production change that saved us for us. So in true field work fashion, and I can tell you, I've worked with Mike in the field, we always want to have a backup plan, and we had a backup plan and had the backup camera even to make it happen, so we didn't drop the ball with the production. So Mike is actually learning something from me from all these years. Finally, I can say he's finally learned something from me. So I'm happy to do that. So thanks to all of you guys for joining us. Your certificates should be coming out in about 2 or 3 weeks. If you're having any issues with those, Focus Remediation Seminars is the place to look. All this information will be out there. So once again, thank you very much. We really do appreciate you sharing this. And hopefully, what you have heard, which is what I have heard, is these guys, Provectus, this technology is just like Kristen Faulkner, right? She waited in line till the appropriate minute to seize the day. And I think we are at that point now where we got this technology running and humming, and we're ready to make the attack, right, at the right moment and leave all the competition for this stuff behind. And more importantly, as you met her, it's a better mousetrap at the end of the day. Folks, I'll leave you with that. Thank you very much. That's it for today.
Thanks again, everybody.
Yep, thanks.
Bye, folks.